So how old is the Earth? Well, we know it's about 4.56 billion years old, but there's a major problem with that number. Our brains can't handle it. We can handle numbers up into the thousands. Once you start talking about millions, it gets a little abstract. And billion, it's just a meaningless number to us. So a major challenge for us geologists is trying to impart to people just what a massive amount of time that is. And toward that end, I've constructed a geologic timeline that is almost 9 miles long. I'm on a road out here. It's 8.8 miles straight line. I'm going to walk it today, talking about the history of the Earth, and hopefully going to impart to you just how crazy an amount of time that is. Come join me. Here I am at the start of the geologic timeline, 4.56 billion years ago, on this conveniently constructed hill marking the very start of geologic time. Now I want to talk to you a little bit about how the Earth formed. It's a really interesting subject and we'll go through it real quick, but I also know that I could do 25 takes and I will forget something important every single time. So we're going to do that via voiceover while we walk a little bit. Our universe is about 13.8 billion years old. With detailed modeling, physicists have figured out how it all formed up to the first 1/billionth of the first trillionth of the first trillionth of the first second. Our own solar system is 4,568,200,000 years old, and we know that from meteorite inclusions. Our solar system formed in an interstellar molecular cloud called a nebula, and at that time we were extremely fortunate that several nearby supernovae were exploding and sending shock waves through the molecular cloud, causing it to collapse gravitationally into several thousand stars. Without those supernovae, not only would our solar system never have formed, but we'd have never gotten the heavier elements that created the Earth. That star cluster broke apart and scattered over the next several hundred million years, and we were ejected from it. And we still see evidence of that in the unusual movement of objects in our own Kuiper belt. Over the course of the next 50 million years, our sun formed and fusion began. The 2% of the material in our solar system that wasn't pulled into the sun formed our planets, with each planetary clump growing by about a centimeter or two each year. A very slow process, obviously taking a very long time. Meanwhile, the area closest to our newly formed sun was way too hot and chaotic for volatile compounds like methane and water to remain, which meant that the planets nearest to the sun ended up being composed of metals like silicon, iron, nickel, and aluminum. Those are your rocky planets: Mercury, Venus, Earth, Mars. Because only about half of a single percent of the nebula that we were composed of was made of those elements, those inner planets all remained small and rocky, while the outer planets where the volatiles could remain became our enormous gas giants that absolutely dwarf our tiny little planet in comparison. This period in time is called the Hadean period, named after Hades because Earth was just a molten, violent hellscape constantly being hammered by asteroid impacts. There probably weren't a whole lot of more violent places in the universe during that time, outside of perhaps a black hole. Those impacts obliterated Earth's very light atmosphere of hydrogen and helium, which is why we have shortages of hydrogen and helium on Earth, despite hydrogen and helium being the most common elements in the universe. Yesterday, I spent 2 hours out here with cans of spray chalk, marking the entire geologic timeline for 9 miles. Last night, we got unforecasted massive thunderstorms, washed everything away. So if you see me in this video staring at my phone from time to time, that's me trying to look for the GPS locations of where there used to be chalk. We're gonna do the best we can out here today. Are you still filming? Yeah. Good, because we are just about at where the moon formed. So at about 4.4 billion years ago, a massive planetary body about the size of Mars crashed into Earth, tore off an enormous chunk of the planet, sent it into orbit. It eventually congealed and became our moon. This massive collision
was absolutely devastating. It vaporized the rocks on the planet so dramatically that for 2,000 years, the Earth actually had an atmosphere made out of vaporized rock. There were thunderstorms where molten lava would rain from rock vapor clouds for 2,000 years. I mean, science fiction hasn't even gotten that crazy yet, and that's what it was like in this hellscape. The Earth, after that collision, was spinning so fast, each day was about 5 hours long. And the moon was about 16 times closer to the Earth at that time than it is now, meaning there were 1,000-foot tsunamis of molten lava sweeping across the Earth. It was just a crazy time. Happily, things calmed down a little bit over the next couple 100 million years. All right, so I don't want to create a 4-hour video. You don't want to watch a 4-hour video. So what I've decided is to try to impart how much time has gone by on this walk without you physically walking it and without you watching for 4 straight hours and making this the most boring video ever. I've decided to set a stopwatch on my phone. So we'll let you know just how much time has elapsed as we walk. We'll tell you the distance we've walked. We'll tell you how much time has gone by. Give you a sense of it. My camera doesn't have enough storage space to record me for 4 hours anyway, so we can't do time lapse either. We'll just be cutting in and out and sharing that with you as we go. So earlier I mentioned just how difficult it is to impart just what a massive amount of time the history of the Earth entails. People try making a geologic timeline, you know, the size of a classroom or the size of a building, but it's still hard to impart. So 8.8 miles, that's the distance of this timeline. Earth, 4.56 billion years old. Would have been more convenient. I learned that the Earth was 4.4 billion years old when I was in college. They've adjusted that time a little bit. If it was 4.4 billion years, how perfect would an 8.8 mile walk be? So every mile is about 500 million years. Every foot we walk is 100,000 years. Every pace of mine is about 5 feet. So 500,000 years, 500,000 years, 500,000 years. That's just how crazy everything is when we're talking about these massive scales of time. By the way, how cool is this shirt here? My neighbor made this for me. I just gotta throw a shout out to her. Best neighbor ever. She gives us all sorts of gifts. Eggs from her chickens. That's worth a fortune in today's dollars. And she knew I'm a nerd. She made this for me. How awesome is that? Thank you, Ryan. All right, well, we got a little bit of wildlife joining us out here. But buddy, you are about 8 miles early. You got no business being right here. See, this is why you don't hire frog actors. Well, we're about 1.1 miles into our geologic timeline now. That puts us 4 billion years before present. We got a long ways to go. We've been walking almost a half hour already. But at this point, the surface of the Earth is cooled enough that you not only have solid crust, you got plate tectonics starting to happen. Things are starting to shift around on a very hot mantle of magma. You even have some very hot, very acidic oceans forming now. They're bubbling pools of acid. It's not a pleasant place to hang out. It wouldn't be a great place to go for vacation. But it does start to resemble an actual planet now, insofar as there's a solid surface of rock that you could technically walk on, and even some probably green colored, very acidic pools of ocean water. 1.5 miles into our walk, about 40 minutes in. Might need to pick up the pace. I gotta pick up my son from the school bus at some point this afternoon. But right now we've got the end of a period called the heavy bombardment period. That's a period where as the name suggests, the Earth is just being bombarded by asteroids and comets and just getting pummeled. While it was a brutal time in Earth's history, it's also not constant. There were probably millions of years in between major asteroid impacts, but it was certainly a lot more frequent than it is now. It's getting a little windy out here, but we're 2 miles into our walk, just a little bit under an hour, and we are 3.5 billion years ago on our timeline. At this point, we see fossil evidence of bacteria and stromatolites. Now, there is indirect evidence of life going as far back as 3.8 billion years, the last stop we made, through carbon-12 isotope enrichment in Greenland rocks. But at this point, 3.5 billion years ago, we do start to find stromatolites. Stromatolites are basically layers of algae that build layer upon layer upon layer as they just keep building themselves up. They just coat rocks. It's basically slime. They coat rocks on any surface they can find, and they build themselves outward. They're not small. Some of these things are larger than a school bus. This is the dominant form of life on the planet, the only form of life we really know about. And they will be pretty much the only form of life on the planet for the next several billion years. We've got a very long walk before we find any interesting life ahead of us. But don't worry, there's some pretty cool geologic stuff too. Three miles into our walk, about an hour and 20 minutes in, 3 billion years before present on our geologic timeline. The core of North America, known as Laurentia, is growing by accretion. Basically, microcontinents are slamming into it. Instead of continuing to slide around like pucks on an air hockey table, they're joining together now and sticking. We have at this time the first evidence of plate subduction happening, major component of plate tectonics. Let me paint a little picture of what the Earth was like in case you went back in time to visit. Bring an oxygen tank with you. There's no oxygen. But it's not that hot out. I mean, it's like Florida in the summertime there. It's warm and balmy. The oceans are especially warm. They're 50 degrees Celsius, about 120 degrees Fahrenheit. But the air temperature's not so bad. You might have expected it to be a lot hotter, but the fact is the sun isn't giving the Earth as much warmth back then as it is today. The way nuclear fusion works and stars is that they produce more energy the older they get. And so, at this point, 3 billion years ago, the sun's only producing about 75% of the energy that it does today. The Earth is only getting about 75% as much light and warmth from the sun. All around you is barren. There's no vegetation yet. The rocks are black or a greenish black, and you have sand where it's been weathered away by rivers. There's no such thing as soil yet, though, because soil is a thing that comes when plants move onto land. It's a foreign world. Very, very strange looking. You've got car-sized stromatolites along the shorelines, but really no life anywhere else. We're at the 3.2 mile mark now, about 2.9 billion years ago, and we have the first ice age that we know about happening. It's the Pongala glaciation, technically 2.85 billion years ago. Now, we don't know whether there were ice ages before that. There's no record of it, but considering how warm the planet was during its early formative years, it seems unlikely that there were. This was probably the first major ice age on Earth. Now, this point also marks a period in time in which the Earth's climate is going to start becoming very unstable. The reason for that is you have life on Earth that only produces oxygen. There's no oxygen consuming life on Earth. At the same time, you have a lot of volcanic activity and a lot of geochemical processes that are gobbling up that oxygen. And so things can swing pretty rapidly from one extreme to the other. We're gonna see a lot of that in the next few stops up ahead. We're 3.6 miles into our geologic timeline now, at about the 2.7 billion year mark. And at this point, I'm really starting to question the wisdom of taking a 9-mile geologic walk in 85-degree weather. At this point though, the core of North America, Laurentia, is starting to really come together. More than a dozen microcontinents have slammed together to form it. And Laurentia itself has slammed into other pieces of land to create a supercontinent known as Kennerland. That continental collision has resulted in a mountain range being established in what we now call the Upper Peninsula of Michigan. Those mountains were called the Devonian Mountains. I shouldn't say they were called. No one was around back then to call it, but they are called now by scientists the Devonian mountain range. Well, here we are, 4 miles in, 2.5 billion years from the present, and about an hour and 45 minutes from our car. We've got an interesting situation happening. First of all, those Devonian mountains, they're gone now. They've weathered away. They've been replaced by the Algoman Mountains, which stand about 9,000 feet tall through the Upper Peninsula of Michigan. Now, this is the start of what's known as the Silurian period, that being named for the Greek word for iron, also sometimes called the Oxygenian period, named for oxygen. The reason for that is going to be real obvious pretty soon. At this point, the supercontinent of Kennerland is beginning to break up, and there's massive supervolcanic eruptions happening all over the continent, breaking it into pieces. As these pieces of continent begin to drift apart, shallow seas open up. And those shallow seas are primo environment for algae blooms. You have massive amounts of algae occurring in these places, and that algae produces a poison called oxygen. Poisonous to plants and poisonous to algae, not poisonous to us, of course, but devastating for the planet at the time. This throws the planet's atmosphere into chaos. Its climate kind of goes out of control because you have algae dumping huge masses of oxygen that cools the planet into the atmosphere, at the same time that you have supervolcanoes erupting, dumping globe-warming carbon dioxide into the atmosphere alongside globe-cooling sulfur dioxide. So it's just a crazy mix, and everything becomes really chaotic at that time. It's called the Silurian period, iron, because as the algae pumps oxygen into the ocean water, all the dissolved iron in the ocean water turns to rust. And that rust sinks down to the bottom of the ocean and creates a layer of red iron oxide. And then the oxygen kind of kills off the algae bloom. And so the oceans become full of reduced iron again. And then the algae comes back and reduces and oxidizes the iron, and you get another layer of red rust raining down, and you get these layers of banded iron formation being created. All of the banded iron formation in the world comes from this period in time. In fact, around this time in ancient Australia, over the course of just 20 million years, 3,000 vertical feet of banded iron formation are laid down. Now I'm going to have you walk with me because we're not going to go very far. We're only traveling about 160 more feet, which I'm not measuring very carefully, but should be up around these tree shadows up here. Right up here, you have the very first of 3 Huronian glaciation events. Now, these are snowball Earth events. These are massive. There is ice all the way to the equator. And this happens 3 times that we know of for sure. And they're absolutely brutal, nearly wiping out all life on Earth. All right, we're 4.4 miles in, 2.3 billion years before present, and this marks the halfway point of our timeline. Whew. I don't know about this. We've got the start of our 3rd and largest glaciation event in the Huronian glaciation period. We've had several ice ball or snowball Earth events happen. But in between them, we've had massive supervolcano eruptions that have warmed the planet, thawed things out, and then things get bad again. Well, this is about to be the worst of them. The oceans are just red with rust, green with algae, and the oceans are completely saturated with oxygen now. Oxygen is being dumped in massive amounts into the atmosphere. That's having an important change because up to this point, methane has been a major component of our atmosphere. Methane is one of the most powerful of the greenhouse gases, far more powerful for warming the planet than carbon dioxide. Well, oxygen breaks down methane. And so with all the oxygen going into the atmosphere, the methane disappears. And we end up with the worst of the ice age events on our planet. Think apocalyptic. 2nd episode of Star Wars, Ice Planet of Hoth. All right, you have ice all the way to the equator, thousands of feet thick in most places. At the equator, the average temperature is 90 degrees below 0, and across most of the planet, 100-mile-an-hour winds whip. How does life survive? Well, just barely, nearly completely extinguished. But along the equator, there are a few places where there are geothermal hotspots, hydrothermal springs that are pumping hot mineral-rich water into the ocean and keeping the ice just thin enough that a small amount of sunlight is able to filter down and keep the algae alive. If that weren't the case, life on the planet would have been extinguished and this video wouldn't be happening. It's a pretty amazing thing. So this marks 4.6 miles into our walk, 2.2 billion years ago. At this point, the ice ball Earth, the snowball Earth is pretty much ended. Another supervolcano has erupted. It's pumped in so much carbon dioxide into the atmosphere that the atmosphere has about 350 times the amount of carbon dioxide that it does today. The melting back of those glaciers leaves the Galgandatilites that people in my region love to find. And shortly after that, the mountains that are left exposed by the retreating glaciers end up weathering and leaving conglomerates made out of jasper and quartzite, which results in the beautiful pudding stones people like to find around here. Before the Ice Age started, during the breakup of Kennerland, a basin was starting to form in what is currently the Upper Peninsula of Michigan, called the Anamiki Basin. That continued to form beneath the ice, but of course not much was happening because it was locked in ice. Now that the ice is thawed, the Anamiki Basin continues to drop and it fills with sediments. But it's still dropping even faster than sediments can collect. 2,000 feet of mud and sand accumulating there, but still it gets deeper and deeper and deeper. The Anamiki Sea is where virtually every deposit of iron in the United States is going to come from. Perhaps not virtually, literally. It is the source of all the iron in the United States. 4.8 miles into our walk, 2.1 billion years ago. And at this point, the Anamiki Sea is now becoming a massive algae colony. And over the next 250 million years, 3,000 feet of banded iron formation is going to be deposited throughout it. All right, now we're around 5.2 miles in. 1.85 billion years before present. The algae growth and the deposits of iron ore have been going full steam for hundreds of millions of years now. Massive deposits, going, but something big is about to happen. In Sudbury, Canada, a massive asteroid 9 miles in diameter comes crashing into the Earth, creates an 80-mile wide crater, raining molten material for thousands of miles, and creating in the Anamiki Sea a 500-foot tsunami that washes right through it, completely disrupting and permanently destroying the ecosystem. Not only will the Anamiki Sea never produce iron ore again, banded iron formations all around the world stop, and they will never happen again. At this point in time, the ecosystems that produce the banded iron formation are permanently destroyed, and there will never be another mineable iron ore deposit forming on the planet. Now, try to remember the stats on that asteroid. 9 miles in diameter, raining molten debris all over the planet. It's going to sound real familiar when we reach the end of the timeline. One more thing I should have added there. This is the start of what geologists call the boring billion. From 1.8 billion years ago to 800 million years ago, they refer to that time as the boring billion, because supposedly pretty much nothing happens on our planet. At least nothing that got recorded. But I think that's quite a misnomer, because there's a lot of interesting things that happened on our planet during that time that we know of. There's probably a lot more that just wasn't recorded because there was so much erosion happening at the time. 5.4 miles in, 1.7 billion years ago, and perhaps the strangest thing to ever happen on our Earth occurs in Gabon, which is in Central Africa. You have the Okla natural reactor starting up. This is a nuclear fission reactor happening in the ground. The ground in that area becomes so enriched in uranium that a nuclear reaction begins beneath the surface and continues for several tens of millions of years, perhaps several 100 million years. I'll have to look it up and let you know. But it's a crazy situation that you can have a natural, geological, self-sustaining nuclear reactor. It's absolutely insane. In North America, you've got more microcontinents slamming into each other, and the Michigan area is a mountain range with mountains regularly standing around 15,000 feet tall. Now I just gotta keep talking for a moment because we're right about here. We're about 50 million years later, and North America, at least the North American Midwest, because keep in mind that we're still talking about the core, Laurentia, of America. It looks like the Himalayas. It's just a massive mountain range, enormous. Now, if you know anything about mountains, they tend to be high, which means there's not much deposition at mountains. There's a lot of erosion. And when erosion happens, the rock record is destroyed. That's a big part of why this period of time is called the boring billion. It's not because nothing happened, but it's because our record of events were destroyed by the fact that at this period of time, there's a lot of uplift in mountain building, which resulted in the rocks eroding away. .8 miles into our timeline, 1.5 billion years before present, and 2 hours and 45 minutes into a pretty tiring walk here. We are deep in the boring billion. There aren't a whole lot of rocks preserved from this time. One thing I forgot to mention at the last stop with the Himalaya type mountains running through the American Midwest, it was because we had collided with another continent to join the supercontinent of Columbia. But here at this point, Laurentia, the core of North America, breaks off and starts drifting off independently on its own as the rest of the supercontinent does its own thing. "6.2 miles in, 1.3 billion years before present, and Laurentia slams into another continent to form the a continent called Proto-Rodinia. And another enormous mountain range builds up across southern Michigan, Ohio, that area there. At modern-day Detroit, there is a mountain taller than Everest, believe it or not. It's called the Silurian orogeny. Now, at about the same time, up in what is now modern-day northern Canada, because at that time, everything was sort of shifted around. It probably wasn't to the north. We have a large mantle plume coming up and reaching the surface. And it is a huge body of magma coming up to the crust. And you have a supervolcano forming called the Mackenzie Large Igneous Province. It is absolutely enormous. While most of the lava rocks it produced have been eroded away over the years, we know that it produced well over 160,000 cubic miles of lava over an area of more than 1 million square miles. It was absolutely enormous. "6.4 miles in, 1.2 billion years before present, and we have two simultaneous massive advancements in life. It's been a while since we talked about any living organisms. We have the rise of multicellular organisms, and we have the rise of sexual reproduction, which biologists believe probably went hand in hand together. Six and a half miles in, 1.15 billion years before present, and about 2 hours and 50 minutes into our walk. We've got Laurentia and Proto-Rodinia slamming into more continents to create the supercontinent of Rodinia, which results in a massive Himalayan-sized mountain range that extends massively through the region. And it's really interesting because it helps us puzzle backwards plate tectonics to see how plates fit together. Because the mountain range begins in northern Mexico, continues up through Texas, follows the Appalachians and the Adirondacks, goes up into Quebec, and continues into Scotland. This is how we know that Scotland used to be a part of Laurentia, the core of North America, before the Atlantic Ocean formed. We haven't got far from the last spot. We're 6.4 miles into our timeline now, 1.1 billion years before present. And a pause in the Grenville mountain building results in extension in the northern Michigan area. At the same time, that massive mantle plume that had fed the supervolcano at the Mackenzie Large Igneous Province has moved beneath the Michigan region. That pushing up of the mantle plume combined with the extension of the crust results in the largest failed tectonic rift, the largest failed ocean building of that ever to occur. North America attempts to rip itself apart, and a rift that extends over 1,200 miles from Wichita, Kansas, all the way up through the Keweenaw of Michigan, back down to Detroit. Over the course of the next several million years, enormous eruptions, unfathomably large eruptions, erupt more than 360,000 cubic miles of lava. I want you to think about that for a moment. A cubic mile, a cube, 1 mile by 1 mile and 1 mile high, 360,000. During the eruption, there were lava oceans more than 1,700 feet deep. This was a planet, well, earlier I compared Earth to the ice planet of Hoth from Star Wars, but how about that planet from the Return of the Sith? I don't know if that's actually the name of it. From the third prequel, where they're on this volcanic planet. Well, that's what it would have looked like in a lot of North America at the time. Absolutely enormous. In some places, more than 40,000 vertical feet of lava were stacked one on top of the other. Now, the Earth wasn't 40,000 feet high. Because this was a rifting event, the ground was sinking. And so the lava flows were going on top of each other and pushing themselves down. So it's more, instead of 40,000 feet high, I want you to think of it as 40,000 feet deep thickness of lava. But absolutely enormous event. But before the continent can completely rift itself apart and form a new ocean, the Grenville mountain building event starts up again, and the extension becomes compression, and basically the crust is pitched closed, and that's the end of the mid-continent rift. One thing I should have added at the time that I was saying that is that with that rifting event, places became further apart. Duluth, Minnesota moved pretty far away from where it started, which was Michigan. This is why the Antimony iron deposits are scattered around a bit. You have a bunch of them in the UP of Michigan, then nothing for a long time as you go west, and then you got some great iron ore deposits in Minnesota. Those were originally the same deposit, but the mid-continent rift opened up right in the middle of that and separated that by hundreds of miles. 6.8 miles in, 900 million years ago. Those of you with calculators who are checking my math might notice I dropped 100 million years in there. There's some rounding errors involved with this timeline, don't sweat it. But here we have the breakup of the supercontinent of Rodinia, and Laurentia, North America, drifts off on its own again. The 6.9 miles in, 850 million years before present, and the first primitive animal fossils can be found. These would be very primitive ancestors to sponges. But we are starting to get animal life, and it won't be too long before we talk about the animals more than the rocks.
"7.3 miles, 700 million years ago. Thanks to the oxygenation event and following another big volcanic eruption in Canada, we have another snowball Earth. The entire planet, maybe except for a tiny zone around the equator, is locked in ice for about 60 million years. Dramatic die-off events, life is nearly snuffed out again. There's a brief thaw, and then another global ice age, a little bit briefer this time.
7.4 miles in, 650 million years ago. Earth is still locked in ice mostly, except for the equatorial zone. But we've got the North American core, Laurentia, slamming into another continent called Pannotia. And that supercontinent is centered on the South Pole. Might be part of why there was such a large ice age happening at the time. Also, in the thawed out sections of the ocean, we have a new form of life evolving, the most advanced life that's ever occurred on our planet, plankton. .5 miles into our timeline now, 600 million years before present, and we enter the Ediacaran period. Life does something new. It gets big, and it gets weird. From what we can tell, everything during the Ediacaran was soft-bodied, and soft-bodied animals don't tend to be preserved well. It's very hard to find very good fossils of soft-bodied organisms. We know that they were weird. There were stalks, there were leafy-looking structures, there were disc-shaped colonial organisms, there were quilted organisms. There were organisms that we can't find a mouth, digestive system, reproductive organs for. We just don't know how these things, for the most part, looked, and we really don't know how they acted or lived. It's a big mystery. But yeah, the reason for that is just the fact that everything is kind of soft-bodied. It wasn't preserved well. At this time on Earth, the days are about 22 hours long. A year is I think a little under 400 days. Yeah, so you're asking me why the days were shorter in the past than they are now. Well, the answer is pretty simple. The moon has been stealing the Earth's rotational energy. As you know, those tidal forces between the Earth and the moon, there's a constant sort of tug of war. And as the moon drifts further and further away from the Earth, it's taking a lot of its energy with it. And so the Earth is slowed down, and it'll continue to slow down in the future as well. But the rate of slowing is decelerating, I want to say. So if you recall, when the moon first formed, it sent the Earth spinning wildly 5-hour days. And then about 1 billion years later, it was 18-hour days. And 2 billion years later, it was 22-hour days. So, you know, most of the tidal forces sort of balancing each other out now. So the moon is kind of stealing less of the Earth's rotational energy than it used to.
7.7 miles in, 500 million years before present, and 3.5 hours away from the car. And we are finally at the Cambrian Explosion.
Finally. All right, so this used to be when scientists thought that multicellular life first evolved, it came about. Of course, we know multicellular life goes back further than that. It goes back to the Ediacaran, and the very earliest stuff goes back before that. But the Cambrian Explosion is still a real thing. Life diversifies wildly. Pretty much everything that lived during the Ediacaran period goes extinct. And the reason for that is the evolution of a new type of animal the planet has never seen before. The predator. Every creature before has either been a scavenger or been photosynthetic or chemosynthetic. They've been harvesting energy from the sun, chemical sources, or they've just been scavenging off of detritus. Now, animals eat each other. Guess what? All those soft-bodied, defenseless organisms from the Ediacaran, they don't do well. They disappear. So this is a period of time where you have a lot of shelled organisms starting to appear. And you got a whole evolutionary arms race. Suddenly, from non-existent to kicked into high gear, as you have the development of rudimentary eye structures for detecting light. Predators use them for finding prey. Prey use them for avoiding predators. You've got new structures for swimming and locomotion, development of leg-type structures. The poster child for the Cambrian is the trilobite. It's just a wild time for life. Well, this stop sign here marks the start of the Ordovician. Either people hate the Ordovician or someone's got a real problem with that stop sign. It's seen better days. We're 450 million years before present, and now we've got some big changes happening. We have the first fish evolving. We've got some modernization of life in the oceans. We've got the first brachiopods and echinoderms, and the very first land plants have started to appear, although they're very, very primitive. Nothing you would probably recognize today as a plant. All along the modern day east coast of North America, you have the Taconic orogeny rising up, another mountain range, precursor to the Appalachians. So at that time, the Earth may have very strangely had a ring going around it. Not a massive ring, nothing like Saturn, but it would have had probably a small ring because at that time, for about 40 million years, we've got something going on called the Ordovician meteor event, where meteors strike the Earth about 100 times as frequent as they do today. So at the end of the Ordovician, we have a couple of extinction events in which more than half of all species on Earth go extinct. And those species that survive tend to be called Lazarus taxa because Lazarus being from the Bible, the man that Jesus rose from the dead, these were species that seem to go extinct and then reappear later in the geologic record, indicating that they survived in tiny isolated pockets, just barely clinging on. The cause of that extinction event, well, It's fluctuating climate, just like it's the cause of almost every extinction event, except for asteroids. But what caused the fluctuating temperature? Well, there's several possibilities. Newly evolved lichens could have been responsible for changing the atmosphere a bit. Volcanic activity, that's always a possible culprit. First land plants, sure. But also, that ring of debris circling the Earth would have reduced the amount of sunlight striking the Earth. Was it just one of those things, or a combination of them? We're just not sure. All right, 425 million years ago now, we're in the Silurian. It's still a time of predominantly sea life. Armored fish and jawed fish first appear. And on land, you've got fungi and bugs starting to make their appearance. Now, the climate during this time is warm and stable. But don't take a stable climate for being a calm climate. Because it was so warm and the oceans were so warm at that time, you had enormous hurricanes and storms that probably dwarf modern day hurricanes, frankly, sweeping across the sea and the land. And it was a pretty violent time to live on the land. 375 million years ago, and we're in the Devonian now. Now, this period is known as the age of the fishes, and fishes really diversify. You get a lot of different varieties of them. You also have very diverse and ecologically rich coral reefs and sponge reefs forming all around the globe. Personally though, I think some of the most interesting stuff happens on land. The very first tetrapods begin to evolve, very early forms of amphibians. Also, plants on land develop a couple of new things. They develop leaves for the first time. They become woody. Material called lignin gives them firmness. And they evolve one more thing they've never had before, roots. And so now they can really sink their roots in, hold on to the ground. That allows them to grow tall. With the combination of leaves, woody lignin structure, and roots, now you have true trees forming, and you've got the first forest starting to go across the planet at the end of the Devonian. One more thing that trees and plants began to do, they first began to, at that time, reproduce via seeds instead of releasing spores the way fungi do. So now you have seed-producing plants. Now this time, the continental core of Laurentia crashes into another continent of Baltica and becomes Euramerica, which is basically the American continent and European continent glommed on together. Now at the end of the Devonian, there's a series of extinction events, with one massive one. What's the cause of that? Well, again, it's reduced greenhouse gases and climate change, just like most of the time. But what caused it this time? Well, there's a bunch of complicated geologic explanations that may have played a role. But I think probably the two new developments by plants, those woody structure, the lignin, and the roots are really what did it. Why? Because these forests can grow much more massive than they used to, and the roots allow the development of a new material on our planet that never existed before, soil. Without roots to hold soil in place, any organic material that fell on the surface just washed away with the next rainstorm. But now that plants are setting in roots, soil gets locked in place. That's great for the forest, but that locks away a lot of carbon. What does that do? It reduces carbon in the atmosphere, and you get another ice age, and you've got an extinction event. Eight miles in, 350 million years before present, and now we're in the Carboniferous. Now in North America, we divide this into the Pennsylvanian and Mississippian time periods, but internationally they just call it the Carboniferous. Named Carboniferous because carbon deposits. So with the development of those woody structures in plants, fungi don't know how to break that down yet. Animals don't digest it. Nothing breaks it down. Sort of like our plastics problem that we have right now where nothing breaks it down. Back then, there was a wood problem. Nothing was breaking it down. And so what happens? Well, they sink to the bottom of the swamps and accumulate. and you get massive carbon deposits, carbon sequestration going on, and all of the coal on our planet comes from this one time period. Every coal deposit, every oil reservoir, every natural gas reservoir, it all comes from this period in time, the Carboniferous. Without this time, there would be no oil, no natural gas, no gasoline. It'd be a totally different world. Now, a lot of people like to imagine that the oil and gas all comes from decaying dinosaur bones and such, but bones don't produce oil and gas. Really, what produces hydrocarbons is plant material in mass. And so the whole idea of dinosaur bones producing the hydrocarbons we use, it was a marketing gimmick from the 1950s that really stuck. People loved that. It all got ingrained in our heads. But it all actually comes from this period of time in the Carboniferous where massive swamps just contained huge amounts of carbon because nothing could break down the dead organic material from the plants. As you might expect for a time period when there's so much carbon sequestration going on, it was actually a fairly cold time on the planet. So the polar regions were locked in ice, similarly to the way they are today. And it was a cooler time in the planet, maybe a little bit cooler than the modern day. .1 miles in. Man, I'm getting tired on this timeline walk. 8.1 miles in, and 250 million years before present, we're in the Permian now. The continents have all slammed together to create the supercontinent of Pangaea. And associated with that, we have a large mountain building event, the Alleghenian orogeny, where the Allegheny and the Appalachian mountains are formed. Now, the Carboniferous was the age of the amphibians. Amphibians were roaming all over the place. But the Permian is the age of the reptiles. Reptiles really begin to diversify. Animals are no longer tied to the oceans and lakes. And thank goodness, because with the closing of Pangaea, there are now vast inland areas with absolutely no water. The climate becomes extremely arid, extremely hot. It's a difficult time to live, but reptiles are perfectly adapted to it with their hard skin that can retain moisture and their ability to lay eggs away from water. Now we're 8.2 miles into our geologic timeline, 250 million years before present. I know I said that just a few moments ago, but I misspoke. Back there, we were actually 300 million years before present. Now we're 250 million. It's the end of the Permian and the start of the Triassic, and something big happens. There's a massive extinction event. 81% of species in the sea go extinct, 70% of land animals go extinct. It's enormous. The cause of that is the Siberian traps, a massive volcanic eruption in modern day Siberia. Whereas Siberia is pretty well frozen today, there are some volcanoes there, but picture a hellscape back then, because over 1 million cubic miles of lava were erupted at that time. Devastated the planet so massively that in some areas it took 30 million years for the ecosystems to recover. The Triassic was still an age of reptiles, but you have a new type of animal evolving, the dinosaur. Oh, this is exactly where we want to film.
All right, I put it on already.
All right, great. 8.3 miles in, 200 million years before present, and we're now in the Jurassic. At the end of the Triassic, there's another extinction event, not as massive as the others, but about 22% of species go extinct. There's a lot going on geologically. The breakup of Pangaea begins. So, hey Ryan, your shirt, beginning of the Jurassic. You've got North America, Laurentia, breaking away from Europe. Europe becomes an archipelago of islands in a shallow sea. North America, as it drifts westward, slams into other continents that glom onto it. And you get most of the land between the Great Plains and the modern day Pacific Ocean sticking on to North America at that point. Dinosaurs are now starting to become pretty common. The age of reptiles is over. Reptiles are still a thing. I mean, they're a thing today, of course, but now we're truly in the age of the dinosaurs. And classic dinos like Stegosaurus and Allosaurus roam the earth. You've got breakup of continents all over Pangea, creating new oceans and isolating populations and really helping spur on diversity and creating a whole range of habitats that are much moister than what you had before, so that you can have life likes water. And so when you have a more moist environment, you have more water availability, life is going to thrive. And the Jurassic is a period where life is absolutely thriving. You've got your enormous sauropods, you got all sorts of theropods, and just most of the dinosaurs that you would think of that pop to your head start occurring at this time and go right through the Cretaceous, which is the next period. .5 miles in, more than 4 hours now into our walk. And we're at about 143 million years before present. It's the end of the Jurassic, the start of the Cretaceous. Now, they used to think there was an extinction event here. We know there wasn't a true extinction event now, but there was a change in life. Stegosaurs and Allosauruses, they go extinct, or they evolve into other creatures. I'm not a paleontologist, so I don't know exactly what happened, but we do know that there was a change in the type of dinosaurs. Almost every single dinosaur in the Jurassic Park movies comes from the Cretaceous, not the Jurassic. So you're talking about your T-Rex, your Velociraptors, your Triceratops. Most of your classic dinosaurs that you thought about all the time as a kid. All right, real professional. I got interrupted by the alarm to go get my kid from the school bus. Luckily, I got someone else doing it. Don't worry, he's not going to be a latchkey kid. But yeah, as I was saying, all the dinosaurs that you thought about all the time as a kid, most of them really came from the Cretaceous. One more thing I forgot to talk about in the Cretaceous. We have the evolution of the first true birds. All right, they don't look quite like modern birds. They've got teeth, which modern birds don't have, but they are looking awfully bird-like. North America gets split in two, not tectonically, but the Western Seaway opens up in right through the Great Plains area of North America. And as far as the dinosaurs are concerned, splits the continent in two. And the isolation of populations actually results in some extra diversity where there are some species that occur on one side of the seaway that don't occur on the other. 8.7 miles into our timeline, and we are so close to being done. 66 million years before present. We're at the KT boundary right now. Thalidomide orogeny is in full swing. Land is being added along the Pacific coast, and that's crunching up the continent. And the Sierra Nevadas are being thrust up, the Rocky Mountains are being thrust up. Also at this time, the first flowers evolved. Now, interesting thing about the introduction of flowers, early on scientists actually thought that the cause of the dinosaurs going extinct might have been hay fever. It sounds silly to us, but prior to that time, there had never been pollen. And suddenly, flowers are popping up all around the globe, choking the air with pollen, something animals have never dealt with before. So the question was, did dinosaur immune systems freak out and did they just die off real quick? Well, the answer to that is no. We now know that at the KT boundary, 66 million years ago, a massive asteroid slammed into modern day Mexico. The Chicxulub asteroid impact was massive. It was a 9-mile wide asteroid. Compare that to earlier when we were talking about Sudbury, Canada. Created an enormous crater. Molten material rained down for thousands of miles. Shock waves vaporized everything within hundreds of miles, probably thousands of miles. And 75% of the species on the planet went extinct, including all of the dinosaurs. But not all the mammals, reptiles, or birds. They clung on. Now we're gonna walk a very short distance, because right around here at the 50 million year mark, birds have decided to fill the ecological niches left by the dinosaurs. Now we usually think about the time of the dinosaurs ending and the time of the mammals beginning, but it wasn't that quick. The birds were way better off to fill those ecological niches than the mammals were, because the mammals were just little small burrowing things, and there was a whole range of birds living above the surface. And so you get things like the terror birds coming about, which are human-sized birds, even larger in some cases, that were as terrifying as their name sounds. The age of the mammals comes a little bit later. One more thing I want to point out about the extinction 66 million years ago is that T-Rex, Triceratops, those Cretaceous dinosaurs, they died 66 million years before present. But Stegosaurus died out 80 million years before them. So in fact, the T-Rex and Triceratops were closer in age to us than they were to Stegosaurus and Allosaurus. It's a crazy thing to think about. We've walked another 200 feet and we're at 30 million years before present now. The climate cools quite a bit and grasslands appear. Grass is a relatively new thing. The first grasslands appear around 30 million years ago. The first primitive grasses pop up towards the end of the Cretaceous. Fun fact, you can kind of decide how accurate a documentary about dinosaurs is if the dinosaurs are walking through grass. You know they haven't done their due diligence, because dinosaurs, for the most part, wouldn't know what the heck grass is. Now, 30 million years ago, life begins to modernize a bit and look a little bit similar to what we're used to, with large mammals coming about. You know, the grasslands were a major thing. So many large mammals graze on grass, and so it was a real boon. And this was the age of the megafauna starting to appear. You get elephants, you get giant sloth, giant bear. Giant mammals start to really dominate, and they continue to dominate pretty much until people come about, and that's probably not a coincidence. We've only walked about 50 feet from our last spot. Now we have the Columbia River basalts being erupted. This was at about 20 million years ago, and this was one of the smallest supervolcano eruptions, but it produced 63,000 cubic miles of lava. That's a lot of lava. You got to remember, even a small supervolcano is a big volcano, and that lava covered a lot of modern-day Oregon and Washington. All right, we're at the end of the timeline, but we're not quite at the end. Every 10 feet is about 1 million years. So I'm about 40 feet from the end of the timeline. 4 million years ago, Australopithecines first evolved. Think Lucy, the very first bipedal ancestors to humans first come about. Let's walk 10 more feet. 3 million years ago, Homo habilis evolves. The first really human-like ancestors of humans. We're gonna walk 5 feet. Okay, we're at 2.5 million years ago, the start of the Quaternary Ice Age that we're actually still in. There's a lot of pulses here, and we're between Ice Age pulses, but we're currently in the Quaternary Ice Age. Let's walk 5 more feet. All right, 20 million years ago, we've got the largest of the Yellowstone supervolcano eruptions. Just really massive. I don't know if I said 20 million years ago or 2 million years ago, but 2 million years ago. All right, notice I've got this handy little device now. We're gonna need it. So 4 feet away from the end of the timeline, 400,000 years ago, Homo sapiens first evolved. The first humans evolved in Africa. And 2 feet from the end of the timeline, 200,000 years ago, humans move out of Africa. All right, let's throw this thing on the ground now and get real detailed. 1 foot, 100,000 years ago. This is the end of our timeline. This is the modern day. 100,000 years ago, exactly 1 foot, the Laurentide ice sheets form. And they cover up all of Canada and a lot of the American Midwest. It took 4.5 hours for us to reach the end of the timeline. But here we are. Smokey the Bear, help us understand geologic time. 50,000 years ago, about 5 inches from the end of our timeline. So right about here. That's 50,000 years ago. That is the really the development of language, navigation, culture, and Homo sapiens. Basically, modern humans really become modern. We show all the hallmarks of modern thought. If we go to the last 1.2 inches, this would be the development of agriculture. In the last inch, 10,000 years ago, the Laurentide ice sheets melt back, exposing the American Midwest and Canada. In the last half inch, 5,000 years, we have the first human civilizations forming. And the last 1/4 inch, that would be the Roman Empire. The last 1/10 of a 1/4 inch would be the founding of America. Let's get out the macro lens here. If we want to get real accurate with this timeline, I get it focused there. That's a human hair. Boy, that ant looked huge through the macro lens. Anyways, I might be on an ant nest here, so I will move. But the last 50 years of your life, if you're over 50, are the width of a single human hair on this geologic time scale. That goes back 8.8 miles, a 4.5 hour walk. Well, thank you for joining us on a trip through the geologic timeline. I hope it was a lot less exhausting for you than it was for us. A big thanks to my wife and cameraman, Jens McLaren. She had to truck it out behind the camera for 9 miles. So thank you for that. All right. Hope you guys enjoyed this video. We got a lot more for you to check out. I hope you enjoy them.